we generate or produce volcanoes and subduction zones. This is schematic model or cartoon shows the basic, very simple setting at a subduction zone, where you have this Pacific oceanic plate here subducting underneath the continental plate. So at this is called the downgoing plate or subducting plate. There are a few very interesting regions I want to mention here. One is this region. This is a wedge-shaped region called the Mantle wedge. The Mantle wedge plays a very important role in terms of the dynamics of the subduction zone, the volcanoes, and the earthquakes as well. At the very tip of the Mantle wedge here, it is called, we call Mantle fault arc. And this is a very special part. This is from the thermal modeling. This is actually within the Mantle wedge, but it's much colder than all the regions around the Mantle wedge. But this colder temperature provides special conditions for some minerals to stably stay there. I'm going to talk about what we can see from seismology. But more importantly is that when you're subducting the oceanic plate underneath the continental plate, at certain depths or deeper than 80 kilometers, the oceanic plate starts to, the temperature starts to increase and it starts to release water into the mantle wedge. With the addition of water within the mantle wedge, the mantle material starts to melt, or the melting temperature is lowered. And then you have magma generation and then erupting at the surface of volcanoes. This is a simple setting, but what we know, what we see usually is a much more complicated setting. One is that subduction zone is not a simply 2D model. It is a 3-dimensional structure. It has a lot of complexity in it. The other is not every subduction zone born the same. Some subduction zone may have a lot of volcanoes, but some may not. This is what we call the segmentation of the volcanism as subduction zones. In Alaska, let's go back to Alaska here. We have a Pacific plate subducting underneath the Alaska or the North American plate. And there's a microplate or smaller scale plate subducting as well underneath the North American plate. But the difference is that this is subducting at a little bit steeper angle, like about 60 degrees, but varies along the stretch. This is more shallower, like 30 to 40 degrees. But this is called a flat subduction. The flat subduction actually has a few very important influences on the surface deformation, elemental dynamics, and the volcanism as well. This is the basic tectonic setting of the Alaska region. But when you look at carefully from the earthquakes distributed, the colored dot here, and blue dot means deep earthquake here, red means shallow earthquake. We look at it along the strike, we see a lot of earthquakes. But the interesting thing is that some of the earthquakes here are deeper than some earthquakes here. Well, that means that we have a lot more deep earthquakes than regions here. But when you look at earthquakes that goes back here, we have more deep earthquakes again. So you also, or the distribution of the subduction zone seismicity tell us about the geometry and seismogenic property of the plate interface. And this also tells us how the plate interface or seismogenic structure varies along the strike. We call that plate a subduction segmentation. However, by studying the seismicity, what we can know is only or mostly the segmentation of the subducting slab or the plate interface. So what we want to know, what we need is the change of the structure, not only the subducting slab, but also the overriding plate, including the mantle wedge and the overriding crust. Inform the volcano distribution that we have a lot of different volcanoes. This here we have the Aleutian volcanic arc, which we have a lot, where we have a lot of volcanoes distributed in a linear pattern. But to central part, we have a volcanic gap. This is still along the Aleutian arc, but does not have volcanoes. And further to the central part, central Alaska, we have two isolated volcanoes. And these two isolated volcanoes are still on the arc, but it is at the very northern or northeastern tip of the Aleutian arc. Further to the southeast in Alaska, we have volcanoes distributed in a more clustered pattern instead of a linear pattern, which is what we see along the Aleutian volcanic arc. In summary, what we see here is that there are a lot of volcanoes, but they are distributed in different density and different patterns, either linear, clustered, isolated, and a volcanic gap. The problem or the motivation for this study is trying to understand how the earthquake distribution or the volcano distribution is controlled by the subduction structure. That's the motivation. What we found, to give you a summary first, is that there are a lot of variations along the strike in terms of the structure of the subducting slab and the overriding plate. And this subduction, this segmentation of the subduction tells us something about the diverse mechanism or volcanism along the margin. And those volcanoes may be controlled by the combination of a mantle wedge dynamics and the overriding crust, in addition to the subducting slab as well. But how do we get this conclusion? I'm going to walk you through in this following slides. We use a tool called full-wave ambient noise tomography. This is the method we use to image the subsurface structure to get the model to understand the structure in the segmentation. And we'll start from basically a very brief introduction about ambient noise seismology. And we have two stations, A and B. There are a lot of signals, a lot of waves passing through the subsurface. But what we received from those two stations are pretty noisy records, except where you have earthquakes. But here is just not having earthquakes. But when you do cross correlation, that cross correlate is two waves. What we see that we can extract the signal that's similar between these two records. This gives us a signal here that traveling from A to B. So in summary, by cross correlating the north record, we extract the wave propagation information between station A and B, and we can use this information to get the travel time to image the velocity between station A and B. There are a lot of techniques that have been developed to really take advantage of this characteristic of the ambient noise cross correlation. And we use a little bit more advanced method instead of a traditional method which use like a dispersion curve to get shear-wave velocity. We use a full-wave ambient noise. The reason we call that full-wave is that first we compute the synthetic Green's functions or the travel time information of the surface wave, where here we use relay waves, from one virtual source, which is a station, to all other stations. This is computed through finite difference methods in a three-dimensional velocity. We start that from a reference velocity. Once you have the synthetic Green's functions, this is what we got from the cross correlation of the noise records, the empirical Green's functions. Then what we do is to cross correlate the synthetic Green's functions with the observed Green's functions. Then what we get is the travel time difference. And because we started from a reference model, this is really most of the cases not the true model. So there must be a travel time difference between one station to others. From this travel time differences, we build up a large matrix using all the station pairs we got, using multiple frequencies to sample different depths. Then from this matrix, we build a relationship between travel time difference and velocity perturbation. The velocity perturbation means that we need to really change the velocity to better match the travel time. Then we invert the velocity perturbation based on finite frequencies. Finite frequency means different frequencies. Like the wave traveling different frequencies sample different depths, different three-dimensional velocity structure. Then after we get the velocity perturbation, we go back and add it back into the initial model. This is the completion of one iteration. Then we start the next iteration to get to update the model. Usually after 4 or 5 iterations, the model converges gradually to have really little change after or between 2 different iterations. That's when we want to stop. Using this method and take advantage of the data in Alaska, where we have a lot of stations deployed here in South Central Alaska, where we covered all the volcanoes we have mentioned at the beginning. And using this data, after 5 iterations, we have improved a lot compared to the reference model. To simplify the reference model, we intentionally started a very simple model, but still 1D. We can do it 1D as well. And this is a very rough model. You see, it shows a very large scale, at least 2 by 2 degrees, because the model resolution is 2 by 2 degrees, but the features in the model are much larger than 2 by 2 degrees. And this is the final model after 5 iterations. The improvements is that we have a better fitting to the phase delays or the phase arrival time compared to the reference model. And the other is that we revealed more details that could help us understand the subduction structure in other problems where I'm going to talk about that. And compared to other models as well, there are a few models that have been published during the past year. This is only 2 models in 2018. There are also a few models in 2019 as well. And this is our model on the top. This is at similar depths from other models. Notice that we review more details. We provide higher resolution compared to other methods. They use a different method. This is all based on using ambient noise, but this is also using ambient noise and travel time from teleseismic events. This is ambient noise at this depth, and so travel time at 75, I think. And by having more details, we're not only providing more details. These details are actually very helpful for our understanding of the tectonic problems. Now I'm going to summarize the key observations in our model. But there are a lot of very interesting features that we can extract, we can talk about, and for other papers. But for this study, I'm going to highlight a few structures. Here, I'm going to show you a few slides to simplify the description. I will do 3 depths at 80, 51, 28 kilometers. This is sampling the subducting slab, structure of the slab. This is the mantle far arc and the uppermost mantle. This is the overriding crust. And this 3 depths will be shown, and I will describe that the main features in 3 regions. One is in the Aleutian-Alaska, southwestern Alaska region, and this is in the south central Alaska and southeastern Alaska region. So remember, the following a few slides, the main features will be described in 3 depths in 3 regions. Let's start from 80 kilometers, where we highlight most of the slab structures as high velocities here. We see here. This is high velocity shown in the blue color, and the warmer color, red color means lower velocity. And this is a Pacific subducting slab. Those are 2 high velocities associated with the Yakutat subducting slab. This is associated with the Wrangell slab. Then one new structure here is this 2 high velocity. From previous studies, this region either was imaged as a single high velocity block, or there are normal velocities. What we received the reviewers are 2 separate high velocities. But this is not only one more velocity, high velocity. They actually correlate pretty well with 2 regions. This is the Denali volcanic gap, and this is the region we have 2 small volcanoes. They do show 2 separate structures, and also correlate or associated with 2 regions with different volcanism. In the back arc mantle, we also see low velocities here, where this is back arc of the Aleutian volcanic arc. Next is the depth sampling the uppermost mantle, including mantle forearc. But what I want to emphasize is the mantle forearc here. This is the mantle forearc along the Aleutian arc. And this only occurs, or mostly occurs south of a latitude of 60 degrees. When you look at along the strike, the velocity is, this is much higher, this is actually normal velocity. This is, we have some low velocity, but the volume is much smaller compared to the Aleutian arc. And this is what and also there are some, at the different depths, this is sampling the arc crust, or not arc, but the crust. What we emphasize is the low velocities along the Aleutian arc crust and the Wrangell arc crust. And this is what we see very interestingly, showing also south of the latitude 60 degrees. But this is right beneath the Wrangell volcanoes. And this is in the forearc crust, not beneath the volcanoes. Those two actually have very important implications on their relationship with the distribution of volcanoes. And there are, so I was talk about a few different depths in different regions. In general, we see low velocities in back arc mantle of the Aleutian arc, actually also in south central Alaska as well, and also some of the Wrangell back arc mantle. And also we see very distinct high velocity subducting slabs in different regions along the strike. Now I'm going to show you 4 vertical profiles along the 4 high velocity subducting slabs to show how different are the structure. I will start from the structure here perpendicular to the Aleutian arc, where we see this is the Pacific slab shown as high velocity. This is earthquakes here, and this is the model plate interface from other studies. And this actually, I didn't mention that, but compared to other studies from vertical profiles, this is actually much better than other studies in terms of the relative location of earthquakes and high velocities. This is the low velocity in the mantle forearc and a little bit of uppermost mantle. The dashed line here is the image, the MOHO from other studies. MOHO is the depth of the crustal mantle boundary. And this is the crustal arc, the low velocity in the crustal arc. This is the back arc of low velocity. But when you go to the Denali volcanic gap here, and we see a completely different structure. See, this is a subducting slab. This is the western branch of the 2 high velocity blobs in south central Alaska. And this is the high velocity within the mantle wedge. This is much higher than what we see above the Pacific slab. And the mantle forearc here is also very different, very high, much higher than what we see at the Aleutian part. But go to the eastern segment, we see a little different structure. One thing is that we see a low velocity here within the back arc. But this low velocity, compared to the Aleutian low velocity here, this is much closer to the volcanic front here. We have volcanoes. We still have a little bit of high velocity here, but we're not clear where or how can we get this high velocity. But it's connected to, I'll show you as the uppermost part of the mantle, of the overriding mantle. And go to, yeah, go ahead.
Your longitude on your top plot there, that arc is going more north, south, east, west. You've got it going as a longitude axis. Is that just turned and you're just conveniently showing longitude rather than the actual direction along the arc, across the arc?
So we, because we want to show that perpendicular to the arc to have some of the structures are in 3-dimensional. So if we, like for the structure, this is the direction, this is the, where we see the subduction from, we want to perpendicular.
So it's more than that, right?
Yeah, if we like do other like latitude or longitude, we'll just have some artificial or visual artificial. So this is Wrangell part, southeastern Alaska. This is the low velocity. This is not as low as those 2 back arc mantle low velocity but this is lower than the surrounding region, where you see a relatively low vertical column here in the mantle wedge above the Wrangell slab. This is a low velocity right beneath the Wrangell volcanic field within the crust. So this is the main structures here. You have seen the very big contrast or change along the strike from different regions along the Aleutian-Alaska subduction margin. And next, I will just want to briefly show you how the structures look like in the three-dimensional space. The blue patches here includes velocities greater than 4.6 kilometers. I use those to highlight the high velocity features, including subducting slabs here, and high velocity beneath the Denali volcanic gap. The yellow and red patches are velocities lower than 4.1 kilometers per second. Use this to show the low velocity features that we have seen that are related or correlated spatially with the distribution of volcanoes. I want you to focus on a few things in the next animation here. One is that this is to focus on the slab segmentation. This is a Pacific slab, this is Yakutat slab, this is a Wrangell slab. The other is I want you to focus on the velocity change of the forearc mantle. This is the mantle forearc here, Aleutian mantle forearc, this is the Wrangell mantle forearc. And this translucent surface here is the modeled plate interface. This is a reference to tell you which part of the velocity is in the mantle wedge and which part are beneath the mantle wedge or within the subducting oceanic plate. So this is I will just stop talking for a few seconds to let you watch that. Okay, it's down. So it's 1 minute of silence. Okay, so what I show you in this animation, you have already seen that there's a very strong segmentation. Segmentation means like the variation of three-dimensional structure in terms of the subducting slab, the mantle wedge, and in the cross, including mantle forearc. This is not showing the cross, unfortunately, to highlight the mantle wedge. So now on a summary here, again, we're going to just to refresh your memory again. So we have different velocities here, and some low velocities in the mantle wedge here in the Aleutian part, but not here. It's very high velocity beneath the volcanic gap. Some low velocity beneath this Wrangell, this central Alaska part, and low velocity here, and low velocity crust beneath the Wrangell volcanic field. And the subducting slab themselves also show very different velocities along the strike.
Take a break for lunch and then start again?
Yeah.
Is that good stop point?
Okay, next will be the tectonic meetings or implications. We can have some food.
Mm-hmm.
Yeah, you can tell later.
Yeah, or you can show the.
Oh, I can leave the animation if you want.
Just keep cycling it.
Yeah, let me see. I
Yeah,
think probably
starting maybe like 5 minutes.
Yeah, let me see if I can just loop around.
You know,
interface there is cutting through the low velocity zone, but that's not how it appears in the video.
You mean this one?
Yeah.
This is like this is a metaphor, but this is probably the oceanic crust. So they are, but they are actually connected. So from here you can see it looks like the surface is cutting through that.
Right.
But there's a very thin, I feel like 10 kilometers or oceanic crust.
Okay.
But we intended to not talking too much about the oceanic crust because it's really pretty thin. But I think that's probably part of the relative to the low velocity, right beneath the, but above the high velocity. Right. Yeah.
Use underscore site. Just put a minus sign in front of it. You use site, and then it takes a string. You do the strings within minus and then the 8-character code. It'll take it out of the solution. It's in fact still there. You just receive it in time series. So that's how you can sort of, and you can, in the blood cake.
Yeah, I hope I can right. Everything okay right now. Yes.
What's that? Oh, I'll get some after, because I can, once he starts talking, I can leave this. So, then I won't have a line. Yeah, exactly. Usually there's plenty, but, if there's not, it means people are really hungry, so it's probably a good thing. Yeah, so the way it works, this is kind of interesting. So I have a guy who his business is he's a vendor broker. So he goes out and finds vendors who can give what we want in our price range. And then if they're late or something like this, he follows up with them. So, so they've been really good because he gives them the spiel, like if you want to deliver at MIT, you get. But right now, because of that construction on the so far you can go
They
being
just
mad
need
at
to
me.
get they just need to get that barrier up, really. I think it is a two-way traffic on it as well.
Right.
It's just a bit congested.
Right, and then so vendors can take a left into that little gate and push the button, and parking may or may not let them through the gate depending on what they say, I guess. But I haven't got enough feedback to know if this is working or not.
What the magic word
But
is.
it should. I mean, if you're making a delivery here, you shouldn't have to drive an hour around looking for parking. It's silly. Obviously, not all the vendors do that.
Should we start now?
Seems okay to me. He's just getting his food. Yeah, go ahead.
It's good now. I think everyone got food. That's very good. Before filling some arm waving ideas, it's better to fill in some food and just occupy your mouth. So anyway, and I have talked about the main features in this model, and now after this brief break, and I'm going to talk about some of the implications. And the first is talking about what the segmentation means. And we have seen a lot of variation of the velocities in terms of the subducting slab, the overriding crust, and the overriding mantle wedge. And here I want to emphasize and put out two in-member interpretations of the segmentation. One is that we see a lot of variations and there's a separation for different high velocity features. This in-member on the left is that those all, it means that we have a broken slabs in different places. They are separated physically by gaps or a slab tear. And the other member is a continuous slab. That means that we have a physically continuous slab, but we have a variation of the strengths. Like there are weakness or weak zones at the places where I see the separation of high velocities. But most likely, in their probably a hybrid or a mix of this the model on the left and the model on the right, at different places. But from the seismic model, we're not able to tell exactly where is the tear, where is the weak zone. But we are currently working on collaborating with people doing geodynamic modeling to see which model matches better about observations from the surface, like GPS observations and some anisotropy or manual flow simulations to understand which model explains better than others. So after that slab segmentation, the next big thing about the implication is our understanding about the mantle dynamics and the volcanic activity. Let's start to form some like mechanisms that control the shear-wave velocities or reduce the shear-wave velocities. We have seen the low velocities within the backrock mantle wedge at some places where we have volcanoes, and we have low velocities right beneath the Wrangell volcanic field. And some low velocities in the mantle forest as well. There are a few ways you can reduce the shear wave velocity. You can have a partial melt, high temperature, you can add water, or the other way is you can have some very specialized mineral called serpentine. This greenish mineral has low velocity, relatively low velocity compared to other mineral prototypes, and it requires a cold temperature and the presence of water. So the chemical reaction when you have cold temperature and water, within the mantle wedge, we form this serpentine, or the process we call serpentinization. Now I want to start from this one. The others are related to the distribution of volcanoes. This is a separate implication. One thing is that this is the presence of a low velocity within the mantle fork tells us very important thing or implication about the hydration status of the mantle fork. When you look at the velocity here along the Aleutian mantle fork, we have low velocities 3.7 to 4.1 kilometers per second. For thermal modeling, the temperature here is much lower than where we see further away from the mantle fork. Again, we have low velocity, cold temperature, and that means we need water ready to get serpentine to have a low velocity here. If there's no water here, the low velocity could be melt or either melt or other high temperature, but this is not the case. We performed some other petrological studies that for this velocity, we have about 20 to 35% of serpentinization. And this is pretty high. This means that there is a high degree of hydration in the mantle fork. This serpentinization gives us an idea about the hydration. But when you look at it along strike, it tells us even more information about how the water input within, or the input into the subduction zone along the strike. There is a lot of low velocity south of latitude 60 degrees. To the north and northeast along the strike, the velocity is much higher. And for here, we see a relatively average velocity. We do not expect the presence of a serpentine here. But we have some low velocity here, which probably has serpentinization occurred as well. But for the volume of a serpentine, it should be much lower or smaller than what we see here along the Aleutian part. that means that there is a strong variation of how much water get into or subducted into the subduction slab. It probably also implicates what is the, or implies what is the sediments input or the hydration status of the sediments. But this need further studies. Our model provides a background, provides structural control on the link between the manifold arc and what we can get into the subduction zone from the oceanic plate. And then there's a lot of volcanoes here along the margin in different locations, geographical areas, distributed in different patterns. Actually, some of them have different magmatism. Now, this is the structure we observe, the chain of structure in different segments again. And now, we have done is we put out a schematic model that compared to the far vertical profiles in far regions. And we're going to go through this interpretation to see how our observation explains the change of volcanism along the margin. I'm going to start from the Aleutian arc, then goes to the Boulder Creek jump down two volcanoes in central Alaska, and then the Wrangell volcanic field. And last, I will come back to the region without volcanoes, the volcanic gap, to see what we can see about the difference. First is that we already talked about the low velocity. Here we have linear distributed volcanoes. And we have low velocities here. Ignore this, we already talked about this for arc. This is the Mantle, uppermost Mantle here, right beneath the Aleutian volcanic arc. To produce volcanoes, I have talked about that in the very beginning. Now you have a melt in a Mantle wedge accumulated beneath the crust, and then it propagates to the surface. That's probably an indication of a melt or melted accumulation in the uppermost Mantle. Now, this actually corresponds to about 7%, some partial melt, about 0.4, I guess, partial melt here, and corresponding to 7% velocity reduction. And this low velocity here, we interpret it to be more likely upwelling, and with subduction of oceanic plate, you will just perturb the Mantle wedge or the Mantle structure here and generate some convection in the Mantle wedge. This upwelling will also bring up some low velocity material, and it could provide or contribute to the magma, but we do not sure because this is really far away from the arc front. It's about a couple of hundred kilometers. What is the mechanism that this could migrate horizontally to here is not clear. So we interpret it to be unlikely to provide a magma to these volcanoes. Then, next thing is about the two separate volcanoes, or isolated volcanoes in central Alaska. Those two small volcanoes are not very active currently. The last eruption was in more than 1 million years ago. But we do have two small volcanic cones. Where we see, this is different from what we see beneath the Aleutian volcanoes, where the slab is about 100 kilometers deep. This is 160 kilometers deep. This is much deeper than what we see beneath the Aleutian arc. Where we have, if you have a deeper slab beneath the volcanoes, sometimes it means the slab is probably colder, or it needs to go to deeper in order to dehydrate and generate a melt. And another contribution of melt is probably the upwelling here. We see the low velocity here, and different from the Aleutian part. This is actually pretty close to our volcanic front. However, we're not able to resolve the migration path of the melt. So the other reason is that because this is not a currently very active volcanoes, the melt or the very sparsely distributed path of migration of melt may not be resolvable by our model due to the limit of resolution. Into the Wrangell volcanoes, we have two very interesting structures. One is the low velocity, the vertical low velocity columns here within the Mantle wedge, and the very low velocities right beneath the Wrangell volcanic field. For the low velocities, we have low velocity in the crust. It corresponds to about 0.6 to 1.1% of partial melt. It also corresponds to the pattern of a cluster of volcanoes were observed in this volcanic field. It probably indicates the presence of a large crustal magma that supply magma to the volcanoes. This low velocity column in the Mantle wedge may be indication of some upwelling or convectional upwelling, and also some edge flow here. And from the slab here compared to the other slabs along the stripe, this actually only penetrates to the depth about 100 kilometers. Others are that we see very clear low velocity actually down deeper than this. This relatively small scale, like shallower penetration of a slab may provide a condition for some asthenosphere flow that could be beneath the Wrangell slab that could flow around the edge, combined with the Mantle convection driven by the subduction that could provide additional melt to this volcanic field. And this is an explanation of the arc mechanism where we have partial melt in the wedge combined with Mantle upwelling, either convectional or from the edge flow, and that could provide a mix of a magmatism. Now let's come back to the Denali volcanic gap. Here, compared to other regions where we have active volcanoes, this shows a very different structure here. Have a very super high velocity within the Mantle wedge. What we know is this is probably the presence of a cold and a dry material here. But we're not exactly know how can we get this one. There are different mechanisms. We can get either depleted or the delaminated, but we're not exactly sure the physical or petrological process that could lead to this extremely high velocities. And to do that, further studies are needed from other studies like petrological studies and probably modeling as well. But at least what we can see is there's no melt in the Mantle wedge. No melt in the crust as well. The crust is not showing us a very low velocity. So the combination of a no melt in the crust and in the Mantle wedge explains the absence of volcanic activity in this region. But we have a very high mountain here. This mountain is not a volcano mountain. It is due to the compression or compressional force related to the Denali fault. Now, we have seen the distribution for velocity structures and volcanisms as well. And now, this is an explanation about why do we have very contrasting volcanic activity in a very close region, a very small, relatively small region. We have it here, there's no volcanoes, but we have two volcanoes here. And this corresponds to high velocity in the Mantle wedge and relatively average velocity here. And this, the lack of volcanic activity in the Denali volcanic gap is commonly attributed to the presence of a flat subduction. With flat subduction, the slab is, whether there are two reasons. One is that the slab goes through a longer distance before it reaches the Mantle wedge. So the water probably already released before it reaches this Mantle wedge. The other is that the slab is relatively flat, so it's not easy to get into the deep enough to be dehydrated or heated. However, this flat subduction hypothesis cannot explain the contrast in between the Denali volcanic gap and those two volcanoes, because they have very similar slab geometry. They have a flat subduction here and here as well. The only difference, or the main difference what we see here, is buried in a Mantle wedge. where we see much lower velocity in general beneath those volcanoes compared to the region beneath the Denali volcanic gap. So that means that what we see that the explanation to the contrasting structure here means that subduction slab is not the only factor that could control the Denali, control the distribution of volcanic activity. So it must need other factors from the minor wedge and from the O'Reilly cross as well. Now I have to talk about that's the segmentation and the implications of the segmentations on our understanding of magmatism. Now comes to the conclusion, the last slide. Now we have observed a much stronger segmentation of the subduction zone, not only slab, but also minor wedge and O'Reilly cross, than previously revealed. These segmentations have very important implications on our understanding about the diverse mechanism. It explains the distribution of different volcanoes, different patterns, and also it suggests that to control the arc mechanism, we need more than just the slab geometry or flat slab or a normal slab. We also need to consider the effects from manual dynamics and the characteristic of the O'Reilly cross. Well, those two may or may not related to the subduction geometry. So this is our study, and I'm free to answer any questions if you have. Thank you.
Okay, let's first thank Dr. Yang for such a very nice talk, and then now we have time for maybe 2 or 3 questions.
Yeah, you talked about upwelling a couple of times in that, low velocity blob that you had in the bottom left of a lot of your plots. How much do you actually think that is really mantle upwelling, and how much could be explained by it just being the core of the mantle wedge, the higher temperatures there?
So this is what
you had a plot of it in one of your slides.
Let's talk more about the Aleutian part. Aleutian is pretty representative. This one? So this is
well, if you go back even further, you had a plot of the temperature profile through that.
Temperature profile.
Yeah, I thought I saw it.
Is this
one?
Oh,
No, keep going back.
Oh, that's talking about the.
There we go. Yeah.
Yeah.
So how much of that blob that you see is actually explained by the temperature there and potentially phase changes in minerals? Is it truly mantle upwelling, or is it just the core of the mantle wedge?
So I think this is like talking about the distance here. This is a little bit further outside of the coverage of this plot. I think this there's a kind of a relatively high velocity compared to here. So for the combination of a low velocity and high velocity, if we have a convection, you have like an upgoing flow and a downgoing flow, there might be velocity difference, but that's possible as well to be like part of the mantle wedge. But this is the whole area here could be the mantle fault, and this could be related to the temperature. That's true. And what we feel like is a little bit further away from the arc, beneath the back arc. It could be, this is location-wise, it could be the upwelling, but it doesn't have to be the upwelling. I think that upwelling is something from models, still from a dynamic model. And we have a subducting slab, there are upwelling, like a convection upwelling generated by the subducting. But you're right, it's possible it could be some temperature change or even some compositional variations. But for compositional variation, we're not able to easily constrain that.
Yeah, sure. Yeah, you could just work it out from the minerals that you expect to be down there at those pressures and temperatures. But yeah. I had a related question just regarding, this is a good slide actually. You have the back arc modeled there, and I wonder if you've considered the effect of extension in the back arc being different in different parts, like the Bering Sea has quite a lot of extension in the back arc, and that's where you see that nice line of volcanoes with the Pacific slab. I'm not quite sure how much back arc extension there is as you move into the Denali area. So could that be something that is also driving that, that source of deeper material helping the volcanics?
Yeah, that could. I think the like extension is kind of similar to rifting, right?
Yeah.
We have an extension. There might be there are two cases. There are either passive extension or active extension. Right? Passive extension, there's something underneath the upwelling underneath there, just to push the plate open. And active is you have extension here. And although there might be some upwelling occurring after extension, but we didn't consider that part as well. And yeah, we're not talking about that, but that's part of the things we can look at.
More an idea for sort of future work. You said you were starting to look at the geodynamic models, maybe with GNSS and things. That could come into it.
Yeah, that's true. That's a very good idea. We have tossed we have done some very preliminary, not me but my collaborators, and very preliminary testing for the dynamic modeling to put in like different materials within the Mantle wedge and below the oceanic crust as well, to see the response of the surface and to see whether they are related. Either we see the, as you mentioned, the back arc extension and also the uplift of the arc. And that's one of the part of the direction, part of the research I'm doing now. But I'm not doing that myself, but I'm collaborating with others to do that. That's a very good question. Thank you.
Thanks for the interesting talk. I have two questions. First one is, you mentioned in the first beginning that there's a subduction segmentation based on the seismicity.
Yeah.
Do you assume that the seismicity next to earthquakes just occur on the slab interface?
Oh, that's for the paper I cited for that. They study only the subduction zone seismicity. So that means they only study the seismicity around the subduction plate interface. However, you have to be aware that there is uncertainties in terms of the earthquake locations, and also, like this is the subduction zone earthquake. They didn't include a crustal, continental crust earthquakes, but you have the potential to include some earthquakes within an overriding plate. So it depends on how accurate is the location. And this is for the plate interface model I use, this is also a fitted. Like you create a surface to fit the location of the earthquakes. And how the surface look like depends a little bit on how the earthquake locations are defined.
Yeah. But the question is that, like in the intermediate depth earthquake, most of or a lot of the earthquakes are not on the interface. They are
Right.
intra-plate earthquakes.
Yes. That's very true. But this is let's see how deep is this one goes before 120. Yeah, I think it's probably around this one and a little bit deeper than that. But again, this is not my study. But this study, they only think about the subduction zone, mainly the plate interface. But yeah, you're right. I think there are people studying like a double Wadati Benioff zone for intermediate depth earthquakes.
Okay, yeah, my second question is, we all know that the cross correlation function is not empirical Green's function. It's not Green's function. So, what's the heterogeneous noise distribution and also the attenuation structure affect your result?
We didn't test that. That's a question need to be quantified. And we have, in reality, the sources and noise sources are not evenly distributed in terms of the azimuthal distribution. That's the reality. But we didn't test how that affects that. But there are some other studies have tested that. This effects on velocity inversion is small. It's less than 1% velocity. But I didn't test that. And the thing I think is you have to get help from a simulation, right? You can simulate the source distribute different azimuth range, and then you can do the tomography using the simulated data to test it, to quantify that. That's a very useful thing to do in the future, but I haven't seen people done that systematically to test the effects on tomography. But definitely the unevenly distributed noise source have influence on noise cross correlation results. Thank you.
Any questions? We don't have any questions. And then so next week we will still have the fish talk given by our alumni, Dr. Lee, Elita.